Okay, welcome ladies and gentlemen to this video lecture. So now finally we are ready to do an example. Let's take a look at this example. So let f be the following function from R to R and define let's define f as follows. F of x is defined to be 2x minus 1, where x is any real number. Prove, using the definition, that the limit as x tends to 3 of f of x is equal to 5. Okay, and now crucially here, using the definition. So we want to prove this statement, but this statement means something very specific. We have to know exactly what it means. So I would suggest, even before you start, write down exactly the statement that you need to prove. So this thing means something specific. What does it mean? It means the following. For every epsilon greater than 0, there exists, that is horribly misspelled, there exists a delta greater than 0, so that if x is within a delta distance of 3, then the function value f of x is within an epsilon distance of 5. So here is the statement that we have to prove. And now, remember what we discussed before. Looking at this, it is very difficult to know where to start. So, where do you start in trying to prove this statement? Where do you start? Remember, where do you start? You start by writing an outline. So I'm going to write here proof, and I'm going to write a scaffolding of the proof. I'm not going to fill in the details as I write it. Now remember, how do we write a proof outline? You look at the statement that you want to prove, and you start at the beginning. We want to prove something for every epsilon. So what do? First thing you do is fix any epsilon greater than 0. Then next thing, what do you want to do? We want to show that there exists a delta. So we have to define delta somehow. And this delta needs to be greater than 0. And what are we allowed to use in defining this delta? We are allowed to use our previously defined symbols. So we are allowed to use, let's add it here, allowed to use epsilon. And that is the only symbol that we are allowed to use in defining delta. Okay, and so now we are done with that part and that part. Then we want to prove this implication. So we want to show that if this holds, so we assume that 0 is less than x minus 3 is less than delta. And now here we want to do some work, and we want to somehow conclude that f of x minus 5 is less than epsilon. So let's write here, we conclude that, or let's add here, under the assumption that we conclude, comma, under the assumption and 0 less than x minus, 3 in absolute value less than delta, that the following holds. Okay, and here we have our proof outline. So this is our plan of how we will proceed. And you see here, this immediately tells you where to begin. So when you look at this statement that you have to prove, it doesn't really tell you where to begin. The first thing you do is write a proof outline, because that tells you exactly what you have to do and what you are allowed to use and where you make your assumptions. Okay. So now let us start filling out our proof. Actually, what I'm going to do is I'm going to copy this page and I'm going to fill it out separately. So let's duplicate this page. I love technology. There we go. So let's write here proof outline, and here let's write our proof. Okay, so now we're going to fill in the details. So what do we want? We want this thing in the end to be less than epsilon. So we are interested in forcing this expression f of x minus 5 to be less than epsilon. So under this assumption, we are interested in this expression. So let's expand this expression. Let's just substitute in what x is, 2x minus 1 minus 5. So that is how f is defined, 2x minus 1. Good. Okay, let's simplify a little bit. This becomes 2x minus 6. Let's factor out a 2. This is x minus 3. Now, let's see here. This part looks suspiciously like that part. But we have assumed that this thing is less than delta. So under this assumption, this expression is less than delta. Okay. However, now notice here, we have control over the delta. We are free to choose the delta. We can define the delta with whatever we want it to. So now we define the delta to force this expression to be less than epsilon. So in fact here, let's think about what we can choose delta as. We want this 2 to go away, and we want this delta to change to an epsilon. So why don't we define this delta as a half epsilon? If delta is equal to a half epsilon, then 2 times delta, which is then a half epsilon, the 2's cancel and we're left with an epsilon. Full stop. And now, lo and behold, we have completed our proof. So we see here we've got this chain of inequalities. We're looking at this expression is equal to this, equal to that, less than that is equal to that. So we have this chain of inequalities, equalities and inequalities. And whenever we have an inequality, they should all be pointing in the same direction. So if we forget about what happens here in the middle, what we finally end up with is this final expression over here. So we forget about what we have in the middle here, and we chain all these inequalities together. This guy is strictly less than that guy. And that completes our proof. Okay, so that is it for this example. We will do a few more examples in the future. I will see you. in a future video.